Okay, and in the last part of our problem, we're now in 2010B, question number 3, which is about an ore containing the mineral tellurite. And that ore is dissolved in acid, and that solution is then reacted with the solution of potassium dichromate. And when it does, it forms telluric acid. And so they gave us the unbalanced chemical equation, and it has several parts. And the first part is identify the molecular ion that is being oxidized. And so if we look at something that's being oxidized, we can go to our Leo. It says GR, which is our little acronym to help us remember that loses electrons is oxidized. Or if you look at the oil rig, oxidation for the oil part, oxidation is loss. And by loss, let's say loss of electrons. So if something loses electrons, it's oxidized. So we're going to go up to the top reaction, and we're just going to kind of inspect everything and figure out which species is losing electrons. And in the meantime, we'll probably also figure out if you have oxidation, you always have reduction also going on. One can't come without the other. So let's go ahead. Now my subscripts have all of a sudden, when I made this a little bit bigger to see, now my subscripts are no longer small. So, but this should be a little 2 there. And so this is a neutral compound, and I have 2 oxygens. This is not one of our exceptions, so we know that this oxygen has an oxidation of number of -2. And since there are 2 of them, this gives me a -4 overall. It's neutral, so it equals 0. So my telluride must be +4. Coming over to my next species in the reaction is my dichromate ion, which has an overall -2 charge. So all of these things are going to equal -2. My oxygen, again, is not a peroxide. It's not attached to fluorine, and it's not by itself. So it must be a -2. It follows those rules, so it's a -2. And if we have 7 of them, that makes this -14. And so I go to my chromium, and I have 2 of those. So 2 times whatever that is minus 14 equals a -2. And so if I do the math and rearrange that, I get each chromium must be a +6 charge. Okay, so now I've figured out everything over here. This is hydrogen ion, so it must be +1. That's the charge is the oxidation number. Okay, now I'm at my telluric acid, and this is a neutral compound, which equals 0. Again, I have my regular oxygen. That's not any one of those exceptions like a peroxide or attached to fluorine or one of those. So I can know that it is going to have an oxidation number of -2. Also, my hydrogen, I know its oxidation is going to be a +1 because it's not by itself. So if I start doing the math, I have 4 oxygens with a -2 charge. That's going to be a -8. I don't know my tellurium, so I'm going to make that an X. And I have 2 hydrogens that are +1, so that's going to be a +2. And so if I add these all up and solve for X, that makes my tellurium a +6. So my tellurium goes from a +4 to a +6. And so if I have something going to a more positive state, it must be losing electrons. So I can write that reaction right here. I'm going to go ahead and after I do that, Well, before we do that, I'm going to go ahead and say this is our +3. The charge is the oxidation number. And water is always -2 for oxygen and +1 for the hydrogen. So those guys are not changing charges, but our tellurium oxide, our tellurite mineral, is the thing that's being oxidized when it becomes the telluric acid. And so we have this is our oxidation half of our reaction. Now part B of that one is give the oxidation number of the chromium. So we can go back. If we look for the dichromate ion, we already found that one. And we said that the chromium in that one, we had 2 of them. And to balance out the charge, it must be +6. So our work for part B is already done. So now comes part C. Now part C is kind of tough. This is one of those more difficult ones. And the only way to do this is to write the 2 half reactions, and we're going to kind of follow the steps for this, and I'm going to add in a little more room right here for that. Let's see. Okay, kind of changed the numbering there, but that's okay. Okay, and so let's go ahead and start this one. Now to do this, we need to write the 2 half reactions. And we kind of started with the first one. We'll look at the oxidation half first. And so if we look at the oxidation half, we have the tellurite mineral, or the tellurium oxide, forming the telluric acid. Okay, and so step 1 would be to figure out how the oxidation numbers are changing and to write the electrons on either the right or the left side. And so if we look at the tellurium, and we know it's going from a +4 to a +6, we must have lost electrons, and so I have 2 electrons on this side, and that balances our +4 from the tellurium originally to our +6 for the after. And so if we add those 2 guys back together, those charges balance. But this is one of those where we have to worry about, this is occurring in acid. And so if you look at this, this is not balanced. And so to do that, step 1 is to balance. After we balance the electrons, which is step 1, step 2 is to add waters to balance the oxygens. And so if we look, we have 4 oxygens here. We have 2 oxygens here. So I'm going to add 2 waters to this side. So now my oxygens balance. I have 2 oxygens here plus 2 oxygens makes a total of 4. On this side I have 4, and so I'm good. And then the last step is, because it occurs in acid, I'm going to add H plus to one of the sides to balance my hydrogen ions. And so I have 4 on this side, and I have 2 on this side, so I'm going to add 2 more to this side. Okay. And so let me double check. If I look, this side is neutral. This side this is neutral. This is -2 charge for the 2 electrons, a +2 charge for the 2 H pluses. So this side also balances not only in charges, but also atoms. So all the atoms are balanced, all the charges are balanced. So that's 1 half reaction. Let me do the second half reaction. Now I'm going to do that one in blue just to kind of keep the 2 straight. So if I look at the other half reaction, I need the reduction. So the reduction half, I have the dichromate ion is being reduced to chromium 3. And so if I look at that, this is going from a +6 before, so that's the oxidation state before, to +3 after. So I must be gaining, or must gain 3 electrons on this side. So my -3 electrons is going to these chromium atoms. Now, if you look at that, I have 2 here and 1 here. And so I kind of need to account for that. So in order to do that, I'm going to go ahead and just go ahead right now and put a 2 here for my 2 chromium atoms. I have 2 chromium atoms on this side. And since I had 2 and they're each a +6, and now I have 2 and they're each a +3, I'm going to go ahead and change this to 6 electrons. So one chromium needs 3, 2 of them need 6. Okay. And so I have added my electrons. The next step is to add waters to balance the oxygens. And so if I look at this, I have 7 oxygens here. And so I need to add 7 waters to balance the oxygens. But now my other issue is I have now added in hydrogens. So I have to add hydrogens to this side to balance the hydrogens. And if I look at that, erase that and give myself a little more room to write. If I look at that one, I have 7 times 2 hydrogens. So I have 14 hydrogens on this side. I need to add 14 hydrogens to the other side. Okay, now let me double check my charges. So on this side, I have 6 electrons, which is a -6, plus 1 dichromate ion, which has a -2 charge. So far I'm at -8 plus 14 positive charges. So I'm a +6 total on this side. On this side I have 2 plus 3, so I'm also a +6. So my elements balance and my charges balance. So now I'm ready to add the 2 half reactions to write the balanced chemical equation. When I do, I look at that, I need to cancel my electrons, and I can't cancel 6 electrons with 2, so I am going to multiply the top reaction by 3. So if I multiply everything in this top reaction by 3, this becomes 6, this becomes 3, this becomes 3, this becomes 6, and this becomes 6. So if I look at my 6 electrons, cancel my 6 electrons. You can never have electrons in the overall balanced equation when you do this. And so now I can pull everything down. I'm going to cancel like things. If it's the same on both sides, I can cancel. So if I look at this, I'm going to look at the waters first. I have 6 waters right here. On the other side, I have 7. So these 6 waters cancel and leave me just 1 water left. And when I look at the hydrogens, I'm going to do the hydrogens, let me do that in this color. If I look at the hydrogens, I have 14 H pluses on this side. I have 6 H pluses on this side. So these 6 will cancel 6 of these, so I'll have 8 left on this side. And so now I can write my overall what's left. I have 3 TeO2, my tellurite. I have my dichromate, forgot my R, Cr2O7, that has a -2 charge. And then I have also 8 H pluses. On this side, I have my 3 telluric acids, H2TeO4. My electrons canceled, my hydrogens canceled. I have 2 chromium 3 ions, and I have 1 water. Okay, and that is my balanced equation. So for that, going back to the top, that was 1 point earned for identifying my molecule that is oxidized. I also could have written Te4+, and that would have been given full credit. In part B, I got 1 point for writing +6 for the oxidation number of chromium. And in this part, this was worth 2 points. I got both points for having a full balance reaction. I could have earned 1 point if I had 2 correct balances among the chromium, the hydrogen, the oxygen, the charge, and the tellurium versus the dichromate. Or I could have 1 correct half reaction with a correct multiplier. In other words, I could have written either this one or this one with a multiplier. But I got 2 points for doing both. Okay. And so the next part is asking me to go a little step further. So let's go ahead and look at the second part. Oh. Okay, in this second part, we are given 46 milliliters of a certain molarity of our potassium dichromate, and it was added to the ore sample after it was dissolved in acid. And then as it progressed as completely as possible, the excess dichromate was determined by titrating with an iron nitrate. And so if we look at this, they gave us the balance equation for that reaction when it was the excess dichromate was reacted with the iron nitrate. And so it says we added 9.85 milliliters of 0.11 molar iron nitrate to reach the equivalence point. So they want to know how many moles of excess dichromate was titrated. Well, if we are given information about the iron nitrate, we know how much iron reacted with the dichromate, so we can do that. So step 1 would be find out how many moles of iron reacted. And to do that, if we take the molarity times the number of liters, we can figure out how many moles. And the molarity that we're given is 0.11 molar, and it took 0.00985 liters, or 9.85 milliliters. And so we have a total of so we have 0.0010835 moles of our iron. Okay, so if we take that if we take those moles of iron and using our mole to mole ratio, for every 6 moles of our iron nitrate, we react 1 mole of the dichromate, which gives us 0.00985 0.000181 moles of dichromate. Okay, so we earn 1 point for either finding the number of moles of the iron or using this mole to mole ratio. And then we earn the second point for having the correct answer for this right here. Okay, part B, right back to the top. Part B asks us to calculate the number of moles that reacted with the tellurite. So this is just our excess. That reacted with the excess dichromate. We want to figure out from the beginning how much we had. So we have to go back and figure out if we could find the total number of moles that were added minus the moles of excess Cr2 of 7, or how much excess dichromate, then we get how many moles reacted. And so if we look at that, part A is this. So we need to figure out how do we find the total moles added. So if we look back at the very beginning of this part, this tells us we have 46 milliliters and the molarity that was added to the ore sample. So that's how we're going to get our moles. So if we multiply the molarity of this times the liters of that, we get the moles. So down here I'm going to write our 0.03109 molarity times our 46 milliliters, except I'm going to convert that to 0.046 liters. That's the number of moles, minus what we calculated in the step before, our 0.000181 moles of our dichromate. That's excess. When we subtract those two, then we get how many moles. And if we do that, we get 0.001249 moles. So that's how many moles of the dichromate. And so we got 1 point for this calculation, how many moles of total that we started with, and then we got another point for the correct answer at the end, which was found by subtracting this first part from part A, or part A from that first part, and now we know how many moles. And the last part is to find the mass. And so if you look at that, if we want to find the mass in grams of the tellurite that was in the ore sample. So what we would do is we would take our number of moles that we just calculated, and if we look at that, for every 1 mole of that dichromate, in the that reacted with the sample, there were 3 moles of tellurite in our ore. And let's just go back up and look at that reaction one more time. So if we come back to this reaction, we found out how much of this reacted. And so if we know how much of this, let's go back to that top reaction right here. We said that for every one, we have an understood one here, of these, 3 tellurites react. And so let's go back down, very bottom, and keep going. If we know the number of moles, then we can easily get to grams. We're not quite there yet. All we have to do is find the molar mass. And so for every 1 mole of tellurite, there are 159.6 grams, and that tells us in that ore sample we had 0.598 grams. And that last point, that last one was worth 2 points. 1 point for the appropriate mole-to-mole ratio, or for the correct molar mass, and then 1 point is for the right answer. So you got 1 point for either this or that, and then 1 point for the correct answer at the end. Okay, great. I will see you guys later.